So we just started chapter 12 last week, and we looked at operations and functions, where we were looking at the different notation that you might see, and then we were looking at the composition of functions. So today we're going to look at inverse functions, what has to hold in order for a function to have an inverse. If it doesn't have those conditions, could we set the domain to make it have those conditions? What does it mean to be an inverse function of one another? How to find the inverse function? So those are things that we're going to look at. So this is, in our book, is 12.2. And we're looking at inverse functions. Okay. So first, let's just talk about notation for inverse functions. So notation, if f of x has an inverse, it is written as f with a little -1, looks like an exponent, and then parentheses x. Okay, so just be careful. This notation where it looks like a -1 exponent does not mean 1 over f of x. So it's not like the same notation where we had exponents with negative exponents. It changed the position if it was in the numerator down to the denominator. That's not what this is saying. It's just notation saying this is the inverse, representing the inverse function of f of x. So this is how you would write the inverse function. And by definition, if f of x is a one-to-one function, and I'll explain what that means in a second. And so just notation for one-to-one, you'll see it as 1-1. So you don't have to write that out all the time. So if f of x is a one-to-one function, and f inverse of x that notation is its inverse. Then the following holds. If you take the composition of f and its inverse, so remember that was with parentheses, f, little circle, f inverse in parentheses x. It doesn't matter the direction you do it, so we could take f inverse of f of x. These undo each other. This is going to give you back x. Another way to write this, the one that I prefer, is f parentheses the f inverse of x, like this. Doesn't matter what order. Only when they're inverses of one another, you're going to get back x. Okay, so let's look at an example to see if two functions are inverses of one another. our f of x, which is equal to 3x plus 2, and g of x, which is equal to x minus 2 over 3. And versus one another. Okay, so we're wanting to show that if we take the composition, doesn't matter which direction we take the composition, that we're going to get the we're going to get x. And so let's look at f of g of x. So that's telling me I'm taking my g of x function, and wherever I see an x and f of x, I'm going to replace it. So this is equal to, I have 3 times, I see an x there, I'm going to put parentheses. I'm going to leave enough room to replace that with x minus 2 over 3. And then I have a plus 2 for my f of x function. But g of x we said was, and I'm doing this a little different than I did before, x minus 2 over 3. So this is 3 all times x minus 2 over 3. Plus 2. And so notice that the 3 in the numerator right here, that we were multiplying by the fraction, cancels with a 3 in the denominator. And we can do that because it's multiplication in between. And so we would be left with x minus 2 from our numerator here, plus this 2 out here. So when I combine like terms, I get back x. So taking the composition the one way, f of g of x, we got back x. So let's try it the other direction. So let's look at g of f of x. So this time, wherever I see an x in g of x, I'm going to replace my f of x function. And so let's write g of x. So I see an x, I'm going to put a parentheses because I'm going to rewrite f of x there. Then I have my minus 2 all over 3. So g of f of x, but f of x is the same thing as 3x plus 2. So I have 3x plus 2, in parentheses minus 2, outside parentheses all over 3. So simplifying, I really don't need those parentheses around the 3x plus 2. So, and I notice I have a positive 2 minus 2, so that cancels. So we're left with 3x in the numerator, all over 3 in the denominator. And so because it's strictly multiplication in the numerator, I can cancel. The 3's go away, and I'm left with x. So since the composition of the functions going both ways are equal to x, they're inverses of one another. So I'm okay with you guys just showing one direction. So really it depends on your instructor. They might want you to show both ways that you're getting back x. I'm okay. If you're going to get it one way, then you have to get it the other way. If for some reason you didn't, then there's something that you did wrong in either direction when you're plugging in the other function into X. Okay, so above I was saying that a function had to be one-to-one in order to have an inverse. Okay. So let's go back and let's talk about what is a one-to-one function. So a one-to-one function well, first of all, it has to be a function. And a function, remember, that had to pass the vertical line test. So for every value of X, there was only one value of Y that corresponded to this. This is actually plus the other direction. So in order to be a one-to-one function, for every Y value, there's only one X value. That gives you that. If it exists. Because there are some Y values you never hit on your graph. And then sometimes your X is not in your domain, so we wouldn't even look at that. And so here you can use the horizontal line test. So for instance, we were just working with graphing quadratics. And so if we had a graph of a quadratic equation and we graphed it, is this a one-to-one function? Why or why not? Okay, so looking at this, it's not one-to-one, or it's one-to-one if for every value of X corresponds to one value of Y, every Y only has one value of X. So let's look at our Y values. So look at this Y value that's right here. And we could choose a different one, but let's say this. Notice right here, here's an X value that gave us that point. And notice right here, there's another X value that gave us that point. So there's two Y values. That give you the same Y. Sorry, there's two X values, not Y values. There's two X values that give you the same Y values. So it's not one-to-one. So again, if I drew a horizontal line anywhere on this graph and it intersects it more than twice, then it's not gonna pass the horizontal line test. So if it passes it more than once, which this passes it twice, then it will not pass the horizontal line test. So you can look at a graph easily to see if it has an inverse, or if that function that you use to graph that has an inverse, by seeing if it passes the horizontal line test. You might be given a set of points and asked, is this function, determine whether each function is one-to-one function. So for instance, let's say you had a set B that gave you a set of points, and in that set, the set of points were, one of them was the 0.62, one of them is the 0.99, another point would be 1.4, and negative 1.5. So I don't know, is this a one-to-one function? Okay, so when I was looking, or we were looking way back in a different course, maybe not, to see if something was a function or not, and it gave us a set of points. A lot of times it's easier if you make a little mapping. So I have an x value here, right, which is 6. I have an x value, let's just go through our x values, that's 9. An x value, which is 1, and an x value that is negative 1. And for every y value, so I have a y value, 6 goes to 2, 9 goes to 9, 1 is going to be mapped to 4, and negative 1 is going to be mapped to 5. And so as long as every y value only has one x value that corresponds to it, then it is a one-to-one. In this case, it is. So if you had had, let's say, the set C, and it had a list of points, so the 0.8 negative 1, a 0.9 negative 1, a 0.117, and 12.2. And they want to know, is C represent a one-to-one function? And so you can either map it like we were just doing above. So 8 goes to negative 1. 9, though, this also goes to negative 1. So right there, I can really stop, because there's two x values that give us the same y value. And that right there tells me it's not one-to-one. So two different x values.
You mean y value? I mean.
So two different x values give you the same y value. So it is not one-to-one. Okay, so now we know what has to hold in order to a function to have an inverse. It has to be one-to-one. That doesn't tell me, though, how to find if the function is one-to-one or not. Or sorry, I guess I can tell if a function is one-to-one. It just doesn't tell me how to find the inverse. So finding the inverse. Okay, so the directions, if you have a one-to-one function, then to be able to find its inverse, this is the following steps. So I tend to like to rewrite it. If it's given to me in function notation, like f of x, g of x, h of x, I tend to first rewrite that function notation as y instead of that. So rewrite function notation as y equals. Instead of that, g of x equals, h of x equals, f of x equals. Once I've done that, what you want to do is you want to swap your x and y values. So wherever you see an x in your equation, you're going to replace it with y. Wherever you see a y in the equation, which is only one place, you're replacing it with x. And so once you've done that, then you're going to solve for y. Once you've gotten y by itself in terms of x, then you have your inverse function. So once you get the equation, y equals in terms of x only. Then rewrite y as f inverse of x. And you can always check, and I might ask you to check on a test or something. Actually, probably not in your class because I'm not really writing them by hand like I normally do. So check by showing either f of f inverse of x equals x or f inverse of f of x equals x. You just copy if you need to. Okay, so let's look at an example. So find the inverse of each one-to-one function. So it already told me it's a one-to-one function. So let's just start pretty simple with a linear equation. So let's say f of x is equal to 1/3 x plus 6. Okay, so I know if I graph this, it's a line. A line is one-to-one as long as it's not a horizontal line. But vertical lines aren't functions. So anyways, so we're going to find f inverse of x. So it first said, let's rewrite this as y instead of f of x is 1/3 x plus 6. And then it told us to swap x and y. So wherever I see an x, I'm replacing it with y, and wherever I see a y, I'm replacing it with an x. So instead, I'm rewriting this as x is equal to 1/3 y plus 6. And now, once you've swapped them, you're going to solve for y. So we want to get y by itself. So you're trying to get the terms with y to one side. In this case, which is easier, there's only one term with y. So I don't want that plus 6 on that side of the equation. And so we can move it over by subtracting 6 on both sides. So we get x minus 6 is equal to 1/3 times y. We can clear the fraction by multiplying both sides by 3. So let's do that. And so distribute our 3. We get 3 times x, which is 3x, minus 3 times 6, which is 18, equals y. So we just found what our inverse function is. So f inverse of x in our case is 3x minus 18. Okay, so let's just check it. Let's show that f inverse of x equals x. Okay, so we know what f inverse of x is. We have it above. Oops. See if I can grab that. Darn it. Okay, it's just gonna be faster for me to write it. I think I have these like cool tools. So we have f of x, right? We had found or was given that it was 1/3 x plus 6. Just so I had them in front of me. And so this told me I wanted to show the way that f of f inverse of x. So basically I'm looking at the following. Taking my f inverse function, which we just found to be 3x minus 8. And I'm going to plug that in wherever I see an x in f of x. So I have 1/3, we see an x, so let's just put a parentheses there, plus 6. So replacing x with 3x minus 8. And then we need to distribute, something's wrong. Okay, well, let's just do it. I'm looking, seeing that I'm not getting x back.
Isn't it minus 18?
Thank you. That's where I knew I was doing something wrong because I wasn't getting x. And I'd have to go back and look, but thank you. This is minus 18. Minus 18. Okay, so distribute the 1/3. So we get 3 times 1/3 x is just x. And 1/3 times negative 18. Well, 3 goes into negative 18, negative 6 times. So minus 6. And then we have the plus 6 out here. So combining like terms, we just left with our x, which we wanted. And so we showed taking the composition of the function and the inverse function we just found, we do get back x. So we did everything right. So what if you were given f of x is equal to 6 all over 7 minus x. You want to find the inverse function. Okay, so again, first thing you do is rewrite it as y equals instead of the function notation. You're going to swap your x and y values. Instead of y equals, it's now x equals 6 over 7 minus, replace x with y. Now we're solving for y. Okay, so we have a rational function or equation, and so we need to get rid of that y in the denominator. And so the only way I see that we can do that is and it's an equation, so we can do this. We're multiplying by our denominator 7 minus y. So the whole point of that, right, was so this goes away. So this does not distribute to the numerator on the right-hand side. And so here though, and I want to distribute my x on the left-hand side. So here we get 7 x minus yx is equal to 6. And that looks like a minus. So we're solving for y again. So let's get to the y term by itself. If we subtract 7x on both sides, we get negative yx is equal to, well, subtracting 7x, those are not like terms. So 6 minus 7x. Almost done. I need to get my y value by itself. And so if we divide both sides by negative x, because I want it positive y. We could, if we wanted to, pull that negative out front. And so this is 6 minus 7x all over x. I technically would prefer that negative in the numerator. So I'm just going to rewrite it, and I can rewrite the order that I add or subtract as long as I hear the correct sign, because this is negative 6 plus 7x. So same thing as 7x minus 6 all over x. So we just found our inverse function. Rewrite y with inverse function notation is 7x minus 6 all over x. Okay, and so our original function, let me just write it here, it was equal to 6 all over 7 minus x. So let's show, oops, that was the original, not the inverse. So to show that they're inverses of one another, doesn't matter. Take the composition in one direction. Oops. Okay, I don't know what just happened. Okay, so I have to look at plugging one in for x, one function in for x. I think I'd rather plug in, I noticed that the f of x function only has one x, where my f of inverse function has two x's. So let's show it by f of f inverse of x. Where this is f of, so my inverse function is 7x minus 6 all over x. So we're going to go back in, and wherever we see an x here, we're going to replace it with f inverse of x. And so this is equal to, so my original function f of x is 6 all over 7 minus x. But instead of x, so I'm going to put a parentheses there. That's where I'm going to replace x. And my f of inverse function is 7x minus 6 all over x. Okay, so I got a complex fraction. So remember, complex fractions, there's two ways to deal with it. Let's get rid of it by multiplying by a fancy 1. Looking at the fraction within the fraction, my denominator is x. So if I distribute x to my numerator and x to my denominator, that fraction is going to go away. And so this would give me 6 times x all over, so distribute the x in the denominator, I have 7 times x minus x times 7x minus 6 all over x. So this is 6x all over 7x minus, so the whole point of that whole thing was so the x would cancel. But make sure you carry that negative. So this would give us negative times 7x, so minus 7x, and negative times a negative 6 is plus 6. So this is equal to 6x all divided by, well, 7x minus 7x cancels all over 6, which is giving us back what we exactly wanted, which is x. So we showed that what we found was indeed the inverse function of our original function f of x. Okay, so I want you guys to notice. So notice that every time that we were looking at the inverse, which was only, we have only done a couple problems, we were swapping x and y values. Recall that x values are representing the domain, the values, and y represents range values. And so if you're swapping your x and y values for one function to get the other, then basically your domain and range are swapped for a function and its inverse function. So notice to get f inverse of x, you are swapping x and y values. The domain and range for f of x and f inverse of x are swapped. This makes the graphs of f of x and f inverse of x symmetrical across the line y equal x. So I'm pulling up Desmos while you finish copying that, and we're gonna look at graphing what we just did for those two problems. Let's graph our original function, our inverse function, and the line y equals x, and show that they're a mirror image across that line. Okay, so I'm going to share a different page with you. Actually, let me hide this. Is there a way to hide that? Okay. Okay, so you guys should be able to see Desmos right now. So let me, and if you don't, then chime in. But let us first let's look at the first one that we did, because that's going to be a simpler function to look at. And so we had our original function was f of x was 1/3 x. Plus 6. So that gives us that graph. We found that our inverse function was y is equal to 3x minus 18. So red is our original function, blue is our inverse function. Well, I guess technically it's based off one another. So let me also graph the line y equals x. Oops. So notice that this green line, if you take this, and it's harder to see, if you take this blue value, I wonder if you can do a point. Okay. Let's look at an x value. It's just that green is so close. Well, let's look at this x value here. This x value here is 9, 0. And so there should be on our graph a point swapping x and y. This is 9, 0. There should be a point on our graph that is at 0, 9. Which if I look over here, this is not 0, 9. What's wrong? Something's wrong. I know why. Because this should have been 3x minus 18. So again, I'm catching my little errors in here because I know things are supposed to be like I'm telling you. So now that I wrote the correct function in here, this should be 0, 6. So any point that you choose on the blue graph, if you swap your x and y value, we can find it on our other graph. So let's look at our y-intercept here, which is 0, negative 18. So that's telling me that I'm going to have a negative 18, 0 point. And so if I look at now on the red graph, that has to be a point, which I see is going to be a point. I need to right there. So negative 18, 0. And so if you have a picture of one graph, then you can easily get a picture of the inverse function graph by swapping your x and y values of your point. So let's look at the other function. So the other function that we had, we had the originally, let's see, 6 divided by 7 minus x. And the other function, f inverse of x, we had in our numerator 7x minus 6, all divided by x. Just make sure I wrote everything down right. And so mirror image. If you folded your paper along that green line, y equals x, it should be a mirror image of one another. So kind of look at this blue and this red line right here. If we folded it, that would lay on top of each other. Same thing over here, this mirror image across here. Again, any point that we choose on one function, then swapping the x and y value has to be on the other function. And so I'm looking at when x is negative 20. Let's see. I know I have a y value of 7.3. So that's telling me I should have a 7.3 negative 20. So if I go over here, 7.3, I'm just going to estimate. So I'm going to go down 7.3. Oops. You see it's almost negative, or negative 20. There it is. And so any x, y gives us another y value. Okay. So let's pause for a minute. And pause. Okay, so let's look at maybe an example where let's say you had, and this is something we've done in the past, or just did. So let's say you had f of x is equal to x minus 2 quantity squared plus 3. And first part, let's say it asked you to graph this. Well, this is already in vertex form. And so we should be able to tell that our vertex is at opposite sign inside. So this is positive 2, same sign outside, so 3. So we have a vertex that is occurring at 2, 3. I see my a value is 1, so it is facing upwards. Okay, so I just wanted a general graph. Part 2 is f of x 1 to 1. And so if you look at this graph, just by the horizontal line test, right? If you draw a horizontal line through this, there's just one, we can just show one case, but there's an infinite number of cases where you could draw a horizontal line and it intersects more than once. And so the answer is no. So limit the domain of f of x to make this a one-to-one function. So if we just say x has to be either smaller than this x value always or bigger than this x value. So we want it so that it occurs that it's a one-to-one function. So a lot of times it's helpful, and you don't have to choose it here, but we are gonna choose it here, to choose either the left or the right of the vertex. And remember, we had this as HK. And so in our case, if we choose X to be bigger than or equal to 2. So now if we graphed our function at our vertex, we have a point at 2, 3, but now it's just going upwards over here. There's nothing to the left of that graph. And so now it's 1 to 1. Okay, so let's talk about the domain and range. So what's the domain and range of our function f of x and our inverse function? Well, we just made the domain for f of x. So let's just kind of make a table. So we have our original function and we have our inverse function. And we just said that we were going to allow our domain x to be bigger than or equal to 2. So x is greater than or equal to 2. So remember our domain and range, because to get our inverse function, we were swapping x and y. And so our range for our inverse function should be the same as our domain. The only thing that's different is when we're talking about range, we use y values. So y has to be greater than or equal to 2. And so our range of our original function, f of x, so notice this is values, our y values. Our y values, we're hitting all y values which are bigger than or equal to 3. And so notice that that's going to be what our domain is. Except it has to be written in x values. So x is greater than or equal to 3. So this is going to be helpful when we know what our domain and range is in this instance when we go look for our inverse function. So D, let's say it says find f inverse of x. Where f of x, when x is greater than or equal to 2 on f of x. Okay, so first thing you want to do is rewrite f of x as y equals. And our equation had been x minus 2 quantity squared plus 3. Then we want to swap x and y. So this is now x equals, see an x there, y minus 2 quantity squared plus 3. So let's get y by itself. So we have a perfect square here. I could FOIL this out. That would make life a lot harder because then I'm going to have multiple terms with y in here and I'm not going to be able to solve. So, and this is a trick. If there is a quadratic with y in here, you might have to put it in this form where you have a perfect square. So you might not have to in this class though. So for now, Let's get this perfect square by itself, and then we can use our square root method to get y by itself. So to get this perfect square by itself, we could subtract 3 on both sides. And so we get x minus 3 then is equal to the quantity y minus 2 quantity squared. Okay, so now we got that perfect square by itself, so we can get rid of that square, remember, by taking the square root of both sides of our equation. And when we took the square root, we had to put that plus or minus there. I'm going to put it there, and I'm going to put a question mark because we're going to come back to it in a second. So taking the square root of both sides, we get this plus or minus the square root of x minus 3 is equal to the square root of y minus 2 quantity squared. The whole point of that was so we could get rid of that square. So we have technically on this right-hand side y minus 2. And I know I have a square root of x minus 3. I just don't know if it's positive or negative. And then maybe we should just put plus or minus here. We'll come back to it in a minute again. So we're almost done. We almost got y by itself. We just have that y minus 2. And so to get y by itself, we want to add 2 to both sides. And so we get y is equal to, which is the same thing as f inverse of x. Adding 2 to both sides, get 2 plus or minus the square root of x minus 3. Okay. So if I graph that with a plus or minus, that's giving me a function, or it's giving me something that's not one-to-one. And this is where knowing what my domain and range of the original function is helpful. So if I have a minus in between the 2 and the square root, what's going to happen is when I'm starting to plug in values for x, which are greater than, in our case, has to be greater than 3, that would give me a positive number here. So if I plugged in 4, for instance, that would give me the square root of 4 minus 3, which is 1. Square root of 1 is 1. So 2 minus 1 is 1. And that's going to give me a number that is not in my domain or range of the other one. And so notice our values always have to be positive. Y is always going to be bigger than or equal to 2 for my inverse function. I found that before. And so I have to use the plus in our case because of the side we chose our domain to be on. If I had chosen x to be less than or equal to 2, then in my case I would have used the minus. We would use the minus for the inverse. So we're going to use plus because the range of f inverse of x was y was bigger than or equal to 2. And so our f inverse function is going to be 2 plus the square root of x minus 3. So let's just, for sake of practice, let's look at the composition of f of x and f inverse of x. So it doesn't matter what direction that you do it in. And so let's plug in the inverse function. Into f of x and show that we get back x. So our inverse function is 2 plus the square root of x minus 3 And we're going to go in and we're going to plug it in wherever we see an x in that function. So our f of x function. So I'm going to leave a space wherever I see an x in a parentheses. So parentheses, I see an x, so another big parentheses. And then after that x, I see a -2. And then the outer parentheses was squared, and then a +3. So let's replace or put in the f of x to square root of x minus 3. Okay, so notice inside that main parentheses, I don't need that parentheses there. There's nothing distributive but a +1. And so I notice that I have 2 minus 2, that cancels with one another. And so since that cancels with one another, I'm just left with my square root inside that parentheses, x minus 3, quantity squared plus 3. It's a single term or grouping in there because of the radical. The square cancels the radical, so you're left with x minus 3, and then outside that plus 3. So this simplifies to just x, and that's what we wanted to show. Okay, so that is 12.2. which were inverse functions. And we needed inverse functions because we're going to get into right now exponential functions. We'll see when we're graphing these in a minute that they're one-to-one. So they pass the horizontal line test, which means that they have to have an inverse function, which is going to bring us to later in the chapter, maybe later this week, looking at log functions. So this was 12.2. Now we're going to jump into 12.3, which is exponential functions. Okay, so we've worked in this class with exponents and simplifying and stuff like that. So you've worked with exponents before. It's the same type of thing. So basically, you have an exponential function if it's in the form of y equals some base b raised to some power x. So b was equal to the base. We have to have a couple stipulations on our base. B cannot be equal to 1, because if you're always raising 1 to some power, you're always getting back 1, and so that's not exponential. The other thing is that B has to be a positive number, so it has to be bigger than 0. And the reason for that is if your base was a negative number, as your exponent changes between even and odd, you would have either positive or negative number. And so that would not be an exponential function. And so if those cases hold, then you're going to have an exponential function. And so let's look at an example. So there's two different types that you're going to see. They're going to be general shape, but a little bit different. And so our base could either be a number between 0 and 1, or our base can be bigger than 1. And so let's look at f of x equal to 2 raised to the x power. And so we can quickly just plot values, points, and see what we get for y. F of x is another way to say y. And so let's say we plugged in 0 for x. So that would be saying that this is 2 raised to the 0 power. Anything raised to the 0 power is 1. So I get back 1 for y. May as well just plot it while we're doing this. So when x was 0, we got back 1 for y. So if we plugged in 1 for x, right, f of 1, you're just plugging in 1 wherever you see an x. You got 2 to the first power, which is 2. So when x is 1, I get a y value, which is 2. If I plug in 2 there, so f of 2 This is equal to 2 squared, which is 4. So if I go over 2, I'm going to go up 4. So I can see that as my powers increase, it's going to start growing pretty fast. So if I plug in 3, I'm going to get 8. 2 cubed is 8. If I plug in 4, 2 to the 4th is 16. If I plug in 5, I get 32. I really don't want to plot these, but you get the idea that it's going to grow faster and faster. So it's going to get steeper and steeper. But let's see what's happening as x is a negative number. And so we want to see what's happening when x is negative. So if we plug in -1, so let's look at f of -1. So this is 2 raised to the -1 power. So again, you need to think about your exponents. Well, if you have a negative exponent, that brings our value down to the denominator. So this would actually just make it 1/2. So when x is -1, I have a y value, which is 1/2. So any negative number I choose is just bringing that 2 down to the denominator, making that exponent positive. And so what's really going to happen is you're going to get 1 over some huge number, and 1 over a huge number goes to 0. So if I plugged in -2 wherever I saw an x, this would give me 2 raised to the -2 power. Well, that's the same thing as 1 over 2 squared, or 1/4. So as x goes to -infinity, as you plug in smaller and smaller numbers, that's going to 0. Notice that there's no number that will ever give you back. You can plug in for x that will give you a negative number, and there's no number that you can plug in for x which would set that equal to 0. So our domain is all real numbers, -infinity to infinity. But our range is 0 to infinity, not including the 0. It's getting closer and closer to 0, and it looks like it's touching, but it's not going to touch. Another way to say that is y is greater than 0. So notice that our function f of x, y equals 2 to the x, if I use my horizontal line test, every x value is only giving me one y value. And so that's telling me, and every y value, it's only corresponding to one x value. So it's a function and it's 1-to-1, so it's going to have an inverse. We're not going to look for the inverse right now. We're just going to look at exponential functions. Okay, so in general, that's the shape of what your graph is going to look like for any value of your base bigger than 1. It's just going to make it grow faster the bigger the base is. So if you had y equals 3 to the x, it would look like that shape, but your y values would be growing faster sooner. And so it's just going to be steeper, faster. So let's look at a number in between 0 and 1 and look at an example of that. And so let's say g of x is equal to, so any number in between 0 and 1, and just to make life easier, I'm going to say my base is 1/2. So we have g of x equals 1/2 raised to the x power, and we want to graph this. And so, oops, I forgot one important point on this last one. I did plot it, but I didn't show it. When x is 0, oh, I did. It was right here. It was 1. Sorry. Let me go back over here. Okay, so when x is 0, anything raised to the 0 power other than 0 is 1. We get back 1. If we plug in 1 for x, right, g to the 1 power, well, that's 1/2 raised to the 1. which is 1/2. If we plug in 2, well, 1/2 squared is 1/4. We're just squaring the numerator and squaring the denominator, or 1/2 times 1/2 is 1/4. So let's see what's happening when we plug in negative numbers. So if I plug in -1, g to the -1 power, this is 1/2 raised to the -1. We can say this is the same thing as the numerator raised to the -1 over the denominator raised to the -1. Change positions to change the sign of the exponent, and so that would give us back 2. So if I plugged in -2, g to the -2. Another way to think of this is if you have a negative exponent with fraction, a single fraction in there, and switch it. So I can take the reciprocal of 1/2, which is 2 over 1, and change the sign of my exponent to 2. So this is 2 squared, which is 4. Okay, so graphing. I see when x is 0, y is 1. When x is 1, I get 1/2. When x is 2, I got 1/4. When x was -1, I got 2. And when x was -2, I got a y value of 4. So if I look at my graph, it looks similar to this. So my domain, I don't have any problems. My domain are all real numbers. My range is the same as the other one. It has to be bigger than 0, or 0 to infinity. And so that shape right there is the general shape of what your function is going to look like if your value is between 0 and 1. So they kind of grow at the same rate. One is either increasing or decreasing though. Okay, so I want to jump to how to solve these exponential equations. And we're going to look at this again and use this fact later on when we get into logs. Okay, so when we're solving exponential equations, there's 2 different types. Ones where we can manipulate the bases to be the same, and some that we can't manipulate bases to be the same. Right now, we're just going to look at the type where we can manipulate bases to be the same. So there's a rule that's really helpful. And the rule says, really wanted it bigger. If you have 2 exponential equations exponential functions equal to each other, so let's say b to the x is equal to b to the y. If your bases are exactly the same, then we can just drop our bases and say our exponents then have to be equal. Then x must equal y. So let's look at some equations. So let's say that you were given 3 raised to the x is equal to 9. and it wanted you to solve for x. So let's use the rule above. And so notice that you can rewrite 9 to have a base 3. And so we can rewrite 9 as 3 squared, right? And so now we can use the rule and set the exponents equal to each other. So then x has to equal 2. So if we had 1/3 raised to the x is equal to 27. So figure out a base that these both can be manipulated and be written in. So I noticed that 1/3, I can rewrite that so that that 3 is in the numerator. And I noticed 27 can be rewritten as 3 cubed. And so both of these can be written in base 3. So usually if I have something in the denominator, I will get it into that base that I want. In this case, it's already that. And so in order to move that 3 up into the numerator, I know I have to change the sign. And so that is 3 raised to the -1 power now. I still have this all raised to my x power is equal to, and so I can rewrite 27 as 3 cubed. So I need to remember my rules of exponents, power to power. And so power to power is multiplying. And so -1 to that times x is just -x. And so I have 3 raised to the -x power equals 3 cubed. Okay, so we manipulated the bases to be the same. So now we can just set our exponents equal to one another. So we have -x is equal to 3. In this case, I don't have x by itself yet. Just divide both sides by -1 and we get x has to be then -3. So a lot of these in this section is manipulating them so bases are the same. If you have 2 raised to the 5 minus 3x power is equal to 1/16. So we want to manipulate bases to be the same. And in this case, I noticed that 16 or 1/16 could be rewritten as 2 to some power. And so let's just rewrite our left-hand side. So 2 raised to the 5 minus 3x power, it's already raised, or has base 2, is 1/, so 16 is 2 raised to the 4th power. but we're not quite the same yet because that 2 to the 4th is in the denominator. I need in the numerator. And so moving it up into the numerator changes the sign of the exponent. And so 1 over 2 to the 4th is now rewritten as 2 to the negative 4th power. And so now we can use our rules of exponents. We have the bases the same, so we can say my exponent of 5 minus 3x has to equal negative 4. So now we can solve for x. And so let's subtract 5 on both sides. And so subtracting 5 on both sides, I get negative 3x is equal to negative 4 minus 5 is negative 9. And then I need to get x by itself, divide both sides by negative 3. So negative 9 divided by negative 3 is positive 3. So my solution is x equals 3. So let's show this is correct. Let's check our work. And so originally we had 2, 5 minus 3x is equal to 1 over 16. And we just found x equals 3. So wherever we see an x, we're going to replace it with 3 and show that this is true. So this is saying 2 raised to the 5 minus 3 all times x, I'm going to put a parentheses where I see that x, is equal to 1 over 16. So I have 2 raised to the, so order of operations, multiply first. So 3 times 3 is 9. So 5 minus 9 power is this equal to 1 over 16. Is 2 raised to the, well, 5 minus 9 is negative 4. Is 2 to the negative 4 power equal to 1 over 16? And it is. And so we showed that what we got is our solution. And I was just doing that just to show the work, not in the case that I had to show it. So there were times, and when we do get into log equations, we are going to have to go back and make sure our solution works because of conditions holding. But our variable, our exponent, doesn't have any restriction. X can always be any real number. And then we set that with our domain. I don't mind scrolling up. Okay, so that is really a lot of what 12.3 is. So I might come in on Thursday or Wednesday, your class is Wednesday. I might come in on Wednesday and just kind of do a quick review or maybe 1 or 2 examples of graphing and solving equations. And we will see that. I'm not sure if I'm going to skip 12.4 for now, which is exponential applications, exponential growth and decay. I tend to like to have information first with logarithms to help us solve more in-depth problems. So I might skip 12.4 and come back to it after we look at logs. So let me pause.